Notes are the first in our unit on sequences and series. As you can see by the name of this notes, we're going to do the first one today, which is a sequence. You've seen sequences before, but you maybe have never heard them called this way. An example of a sequence would be something like 2, 4, 6, 8, 10, so on and so forth. This is a pattern of numbers, but this is also a sequence. Well, how did I get from each number? How do I keep the pattern going? Well, from 2 to 4, I added 2. From 4 to 6, I added 2. 6 to 8, I added 2, and so on and so forth. So I could keep this list going by going up by 2 each time. Let's do another one that starts with 2. What if I said another sequence is 2, 10, 50, and 250? This one's maybe not quite so obvious, but if we think about it here for a second, to get from 2 to 10, I could either add 8 or I could multiply by 5. To get from 10 to 50, I don't add 8, but I do multiply by 5. And again, here I multiply by 5. So I could keep the pattern going if I wanted by multiplying by 5. So this leads us into the idea of sequences. A sequence is essentially a list that has some sort of pattern that we can figure out. Just like the different functions that we found before, a sequence is a function, so it has a domain and a range. The domain of a sequence we call the set of natural numbers. The natural numbers are the counting numbers, 1, 2, 3, 4, so on and so forth, and sometimes we'll include 0. The range is what we call the term. So we're rarely going to call it the range, but we call these terms. So if I go back to my list, the first term was 2. The third term in the first list was 6. Let's say I asked you to find term number 6. I would take term number 5, which was 10, add 2, and get my next term to be 12. So each term has a number, and then that number is a value. So the term of a sequence is what we call the range elements of our functions. The different elements that we call terms, we denote those as A1, A2, A3, and then wherever we choose to stop goes up to AN. So again, my third term, we would call this A sub 3, A3 is equal to 6. As we go to talk about sequences, there's a couple type of sequences and a couple of different ways that we can describe them and work with them. The first way is that this list either can go on forever or we can cut it off. So a sequence can be finite, means it has an ending point, or it can be infinite. The list goes on forever. From there, I have a list. Our goal in this section is not just to make a list and find the next number, but it's to create rules behind them so that I could find the 100th term in the sequence without having to write out all 100 of them. And there are two ways to do this. I could find any term in a sequence by using what we call a recursive sequence. And a recursive sequence depends on the previous term. So in order for a recursive sequence to work, I have to know the term that was right before it. But let's say that I don't want to do that. I can also create what is called an explicit sequence. And those can be found using a formula. And for example, if I wanted to find the 100th term, I should just be able to plug the number 100, work through the formula, and it gives me the answer. Last ways that we'll categorize sequences. Sequences, as we look at the trend in the numbers, there's pretty much two directions it can go. Either those values are going to get closer and closer to a specific number. That is called a convergent sequence. Or the numbers are just going to have they're going to head towards they don't head towards a specific number, and they might grow really, really large or really, really negative, and this is called a divergent sequence. So here, this is our summary so far. There's a lot of new vocabulary, and we're going to look through the next couple of examples to see how it all works. As a quick disclaimer, when it comes to the note sections, it is up to you to self-pace until you understand. I will work through a variety of examples that will show you the different skills that you need. If you feel like you understand, you're welcome to move on to the practice set. That's what you'll be turning in. if you feel like you need to watch again, the video is there for you to use as a reference. So let's look at a couple of examples. The first one is the most basic way that we'll work with a sequence, which would be finding the next terms. So here's our sequence. It goes -7, -4, 1, 8, 17. They ask us to find the next 4 terms. Well, now it's up to us to determine a pattern. I usually start with either addition or subtraction or multiplication and see if I can find some sort of pattern. So let's look here. To get from -7 to -4, I added 3. I can't think of a clear number that we would multiply, so let's start with addition. To get from -4 to 1, I don't add 3, but I do add 5. So those aren't the same numbers, but let's try something else. If I go from 1 to 8, I'm adding 7. Maybe you're starting to see a pattern develop here. Let's see if the pattern continues. I go from 8 to 17, and I add 9. Interesting. Okay. Here's what I'm noticing. It looks like the pattern is these are going up by adding the next odd number each time. So if I wanted to find the next 4 terms, this term is A1, -4 is A2, A3, A4, A5. So the next term would be A6, and A6 would be, I would have to take the term before, 17, and I would have to add the next odd number, which would be 11. So that makes term A6 28. So the next step, what we're going to do is we're going to find the 7th term. What we're doing right now is a recursive sequence. I'm taking the term before, so I take right before 28, and I'm adding a new rule onto it. So if I added 11 last time, this time I would need to add 13, and then I do 28 plus 13. That gives me my next value to be 41. All right. I want you to take a second, see if you can finish these. If you want to pause the video, try to get the next 2, and then I'll do the next ones from here. So next up, we have the next term, which is at this point, term A8. So that would be 41, and then what are we up to? We've done 11, 13, so next is 15. 41 plus 15 gives us 56. So we've got 3 terms, they want the next one. So then for A9, that would be term A8, 56. This time we're adding 17, and that gives us an answer of 73. So if we wanted, we could have just written in a list following after 28, 41, 56, 73, and the pattern continues from there. So this is the first one, find the next terms in the sequence. Let's go on. What I will do is I'm actually going to skip the next example for right now, show you a couple others, and then if you would like to see another example of finding terms in a sequence, I'll come back to it at the end. All right, let's go on to the next type of thing. So the first, we found terms in a sequence, we followed the pattern, and then we applied that pattern to the rest of our numbers. We'll come back to number 2 later. Number 3 it asks us to find the 4th term of the explicit sequence, and they tell us that an is equal to 2n squared minus 3. So this is an explicit sequence. This means if I want to find the 4th term in my list, so this term right here, I just need to plug in 4 into my list. So the 4th term means that n is equal to 4, where n means whatever term that we're on. So for this one, the 4th term, which is a sub 4, its value will be 2, and then times 4 squared minus 3. They're telling us that n is whatever term we're on. We plug that number in, and then we evaluate from there. Let's follow order of operations. We need to square the 4 first. So this becomes 2 times 16 minus 3. Multiplication next, 32 minus 3. That gives us an answer of 29. So as a quick reminder here as we move forward, n is the number of the term in our sequence. So whatever number we're at in the list. So we were at the fourth term, that makes n 4. An is the value of the nth term. So the fourth term, or the 100th term, or n being general, we can make an equation. Now that we've looked at an explicit sequence, let's look at an example of a recursive sequence. First, let's notice how it looks a little bit different. They tell us that a1 is equal to 3. That means the first term is 3. They also tell us that an, any nth term, whatever it is 3 times an minus 1 minus n plus 2. Let's break that down real quick. This an minus 1, all that means is the term right before it. So if we're looking for the 100th term, we would need to do 3 times the 99th term, and then minus, n just means the number term you're on. So if I'm on the 100th term, it'd be minus 100 plus 2. Here's the challenge with recursive sequences. In order to find the fourth term, I need to know what the third term was. We have to trace our way back to the beginning. So let's get started. Here's one thing to pay attention to. They tell us that n is greater than or equal to 2. So we're starting our list when n is equal to 2. So let's start there. And then that would be the first term number. So we're going to need to go up from there. So when n is equal to 2, we're going to use a1 to figure that out. So term a2 would be equal to 3, and then a1 would be an minus 1. So that'd be 3 times 3, that term before it, and then plus, we said that n was 2. So minus 2 plus 2. So let's work this out. That would make this 9, and then minus 2 plus 2 equals 0. So it just makes a2 come out to be 9. So as we go up from here, when n is equal to 3, that's our next term, a3. So that would be 3 times a2 minus 3 plus 2. So then that makes this 3 times, well, term a2 we just figured out was 9. 3 times 9, and then minus 1 when we do the 3 plus 2. So that gives us 27. 3 times 9 is 27 minus 1, so that gives us an answer of 26. So now we've found the second term. The first term is 9, the second term is 26, so we have to do this 2 more times. So next up, we have term a4 would be 3 times term a3, the term right before it, minus n, which is 4 plus 2. As we go, hopefully the pattern becomes easier to see. So this is 3 times 26, which is the answer of our term right before, and then minus 2, which would be equal to, let's see here, 3 times 26 is 78, so that should give us, I think here, 76. Let's check that real quick. 3 times 26 is 78. Minus 2 is 76. Awesome. Okay. And then next up, we have our last term, our fourth term. Pay attention here, since we're starting on 2, the fourth term is happening when n is equal to 5. That's the fourth number in our list, since that we're starting at n equals 2. So that's 3 times a4 minus 5 plus 2, which is 3 times 76 minus 3. Let's see here. 3 times 76 is 228 minus 3 gives us 225. And that would be our final answer. We've got 2 more things to look at before we finish. Next up, we're going to look at a sequence. We are going to write both an explicit rule and a recursive rule. You'll see the differences, hopefully, with this. So next up, it asks us, given these numbers, 2/5, 2 over 25, 2 over 125, 2 over 625. I want to give you a second here, and I want you to pause I want you to figure out how I'm getting from one term to the next. Hopefully you figured that out. Here's what I see. To get from 2/5 to 2/25, I was multiplying this by 1/5. So each time we're multiplying by 1/5. This would be a good way to get our recursive rule. For the recursive rule, we need two things. We first need to know where we're starting. So the first term, a1, would be 2/25. So we've defined it that way. And then next, as we go, we need to make a general rule for any term. So let's think about if I knew that this was 625, this was the previous term, how would I get to the next term? Well, we said we figured out that we would multiply it by 1/5. So this would be 1/5 times the previous term. The way we write that is a n minus 1. This just denotes for us that we are referring to the previous term. So in that case, if we knew that the previous term was 2/625, we'd multiply that by 1/5. So what we have here in pink, this is a recursive rule, the first term and then our general rule. We do need both pieces. Now let's do an explicit rule. This will show the difference here between the recursive and the explicit. The goal is that if I say that this first term is happening when n is equal to 1, if n is equal to 2, when n is equal to 3, and so forth, I want to be able to plug these numbers 1, 2, and 3 in somewhere to get an answer. There's a lot of ways to think about this as we find patterns. This is all about finding the pattern, and here is how, I'll move this above, here is how I would go about thinking about this. These numbers here on the bottom, 5, 25, 125, those are all powers of 5 that are going up. So I could think about 5 is 5 to the first power, 25 is 5 squared, 125 is 5 to the third power, 625 is 5 to the fourth. Maybe we're starting to see this. I see a 1, 2, 3, 4 showing up as the exponent. So I could say that I see my rule showing up. For the explicit rule, the nth term could be found. Well, if I wanted the 7th term, there's a pattern here where every single time, what shows up on the top? It's a 2. That did not change. But what did change was the bottom. And we were taking the 5, and when n was 2, I was plugging in 2 for the exponent. So if I wanted the 7th term, I would plug in 7 for the exponent. So that would make this come out to be an exponent of n. Let's try it out. Could we get the exact same thing if we do a test? If I say that the 4th term, a4, is equal to 2/5 to the 4th power, that's 2. 5 to the 4th power is 625. So that comes out to 2/625. So that does work. So my explicit rule is what we have here. An is 2/5 to the n power. This is really powerful because it allows us to find any term we want. I could now have you find the 1,000th term. This number is going to get really big, but we could find it. Okay. Here's the last thing that we're going to do today is we need to determine if a sequence is convergent or divergent. A reminder that convergent heads to a number, divergent does not. And so as we work through here, what we're going to do is we are going to use the table feature to figure this out. So you will need your graphing calculator, and hopefully you have access to this. I have it reposted for us here. First, already since it's off, I'm going to make sure that my plots are off. Remember, we don't want those. What we're going to do is we're actually going to go in and we're going to graph this value. So this would be 4,000 times -1/4 to the x power. Now I've showed you where to find the table before. If you look before, the table feature is right above graph, so we click second graph. and it takes us to the beginning of our table. What you want to do is you want to start, and at this point we can just examine, we can start scrolling, and we can figure out what's happening to the y values. As I look up from 1 to 7, the numbers are alternating between positive and negative, but if I look at the number, you should see that it's getting smaller. So these numbers are getting smaller. It becomes 0.003, and then 0.06, 0.01, 0.003, and then it switches to this e to the negative. That's scientific notation saying this is getting to a really, really small decimal. The -3 means there's be 3 zeros, -5, 5 zeros. These are tiny numbers, and we say tiny numbers are really close to 0. So the further we go out, the better we can figure out that this is heading towards 0, which allows us, going back over to our notes, this is a convergent sequence, and it is the numbers are heading towards 0. Let's look at a second example. The next one is -2 to the n power over 2. For this one, I have -2, and I forgot to say this before, we are going to make the exponent, we're just going to write x. It's not an n, but x stands for our variable, and that works here. And so I write -2 rather than to the n power to the x power, divided by 2. I'm going to go back and I'm going to examine my table. Now, unfortunately, it starts us off where we were before. If you want, you can scroll back to the beginning. And let's look at what's happening to our numbers. As I can go backwards, I see they're getting smaller. As I go forward, I start at -1. They're oscillating between positives and negatives. But if I look numerically at those values, those are getting bigger and bigger and bigger. Is there some common number that's heading toward? No, it just looks like they're going to continue getting bigger. And whenever you get to this E notation, if it's positive, it's just adding a lot of zeros on. So this would be a divergent sequence because the numbers are getting very large. They're not heading towards some common value. As a tip, if it's convergent, you'll usually find the numbers are going to head toward one specific smaller number. Maybe they're getting close to 0, maybe they're getting close to 1. You'll start to notice this as you look at your values. I would encourage you to take a look at it. If you properly plug this one in, don't forget to type parentheses around your denominator. This function will also come in to be convergent. So this is the end of these notes. If you would like, you can pause now. I'm going to go back up and talk about number 2, finding the next terms in the sequence, but you're welcome to end here and go over to the practice set from here. So for those who are interested, here's number 2. We're going to find the next 4 terms in this sequence. Again, we need to figure out, if I remind you from the beginning, we are adding these odd numbers that were going up. If I look to go from 81 to 27, what I noticed that I divided by 3. I divided by 3 to get from 27 to 9, and I divide by 3 to get from 9 to 3. So it looks like to keep going, I'm going to divide by 3. So for my next terms, 3 divided by 3, well, the term following would be 1. I take 1, I divide that by 3, and that becomes 1/3. I take 1/3, and I divide it by 3. And again, it makes my denominator bigger by 3, so it would be 1/9. And if I take 1/9 and divide by 3, that becomes 1 over 27. Hopefully we can see here that the more we keep dividing, that fraction is going to get smaller and smaller, and we could think of this as being a convergent sequence because these numbers are going to get really small, which makes them really close to 1. So that's the end of section 10.1 on sequences. If you need to, go back and watch this again.